Hello, welcome back to Finite Element Methods, and today we are going to look at steady-state heat conditions. So before we start with how we can use finite element in solving heat transfer problems, which is in most of the lectures that we have looked in the previous videos before, which is how we can solve the structural problem using finite element method. But in this case, finite element is not only can be used for structural analysis, even though its first intention was to solve a structural problem, but nowadays finite elements have a broad capability not only for solving structural problem. We can use finite element for solving fluids dynamic problem and also heat transfer problem as well. So before we start with heat transfer and solve it using finite elements, I think it is better for us to look at a brief introductions to the heat transfers. Heat transfer is a discipline of thermal engineering that concerns with the generations, use, conversions, and exchange of thermal energy, or in another name we call it as heat, between physical systems. Heat transfer is classified into various mechanisms such as thermal conductions, thermal convections, thermal radiations, and transfer of energies by phase changes. So engineers also consider the transfer of mass of different chemical species, either cool or hot, to achieve heat transfers. While these mechanisms have distinct characteristics, they often occur simultaneously in the same systems. So heat transfers are also known or called as diffusions. So which is a direct microscopic exchange of kinetic energy of particle through the boundary between two systems. So when an object at a different temperature from another body or its surroundings, then the heat flows so that the body and the surrounding reach the same temperature, at which point they are in thermal equilibriums. So such a spontaneous heat transfer always occurred from regions of high temperature to another regions of lower temperature, as described in the second law of thermodynamics. So heat convections occurs when bulk of flows of fluid, gas or liquids carries heat along with the flow of matters in the fluids. In this case, the flow of fluid may be forced by external processes, whether by fan or other means, or sometimes in gravitational fields, which is by buoyancy forces caused by thermal energy expands the fluids. For example, in the fire plumes, thus influencing its own transfers. So the latter process is often called as natural convection. So we have two terms here, which is the first is the forced convections, and the latter one, which is known as the natural convections. So all convection processes also move heat partly by diffusion as well. So another form of convection is a forced convection, as I mentioned just now. In this case, the fluid is forced to flow by use of pump, fans, or other mechanical means. The fundamental mode of heat transfers are three. The first one is known as the conductions. Number two here is through the convections, and the third one is here is through the radiations. So and this process actually can occur in steady state and also in transient conditions. So for the first example, which is the conduction, which can be represented by the first figure that we have here. So what is conduction here? Conduction is actually, or sometimes also known as diffusions. So it's a transfer of energy between objects that are in physical contact. For example, here we have a rod which is in physical contact with the heat source. So in this case, thermal conductivity is a property of materials to conduct heat and evaluated primarily in terms of Fourier laws for heat conductions. So in the first example here, as we can see here, I have a rod which is I clamp it there, and then I apply or put this rod in contact with the source of heat at this particular point within my rod. So after for this rod exposed to this source of heat for sometimes, then we can see that if we put the temperature the thermometer at different point along this along the rod, then we can found that the heat can be sensed along this rod but with different temperatures value. So that means here the heat can travel through the certain material, especially the material that has thermal conductivity. So different material has a different thermal conductivity value. So the highest the conductivity value, that means it will be easy for the heat to transfer within the rods that using that particular materials. So the second example or mode of heat transfer, which is in this case known as the convection, and it can be represented by the second figures in this slide. So in the convection process, the transfer of energy between an object and its environments due to the fluid motions. So in this example, we have we would like to boil water in this kettle. So the heat source is applied at the bottom surface of this of the kettle. So after for some time, when the heat is conducted from the heat source to the material at the bottom part of the kettle, where in this case we have here, which is where we have the high temperature regions, and the water initially, which is the low temperature regions. So actually there is a conduction process occurs in this boiling of the water, and after some times we boil the water, then the bubbles start to develop at the bottom of the kettle, and later on after that it lifts up from this surface from the bottom part of the kettle surface, and lift up to the surface of the water level. So in this process, actually the heat that contained in the bubble will be convex will force the convections in this boiling water process, because the bubble itself is also carry the heat from the heat source. While the last mode of the heat transfer is known as the radiations. So the radiation is a kind of heat transfer, or the transfer of energy by the emissions of electromagnetic radiations. For example, we are actually our Earth is thousands of kilometers apart from the sun, but the sun here is actually the source of heat that can that somehow transfers this heat, the heat. So the sun, that is the huge source of heat, transfers this heat source, the heat to the earth without any contact. So this is known as the radiations, or electromagnetic radiations process. So in these lectures, we will limit our discussions on the one-dimensional steady-state conduction process, which is actually these heat transfers are also or in real life occur in a three-dimensional space. So that's mean here the heat transfer in all three space direction. That's mean in x-axis, y and z-axis. But we put the limitations on our discussions here just for 1D steady-state conductions. So in this case, in one-dimensional problem, the temperatures gradients exist only in one coordinate axis only. So for example, if we take our axis of consideration, which is x-axis, so that means here the heat will transfer in this x directions only. So in this case, that means actually in reality there will be the heat that's transferred in the z and in the y direction, but in our case, since z and y is very small regions, so we ignore it in this case. So in this case, we just consider how much the heat will transfer from point to another in one axis only, which is in this case in the x directions. So in terms of objective, our objective here is to analyze the temperature distributions within the body, and also how much the amount of heat transfers or heat flux occurs within these bodies. So now let me first look at the theoretical part of the heat transfer problems. So we start with the governing equations. Consider heat conductions, which is given by Q. The unit is a watt per meter squared through a plane wall as shown in this figure. So my plane wall here actually just shows the cross sections of my wall, which is in 3D it will look something like this. So this plane wall actually consists of 6 faces, but the most important faces, which is the one that resides on the left and the right face. So assuming that there is a heat flows across this controls of this sectional area of my wall, and from there I would like to, for example, come up with the energy balance crossing this plane wall. To generate the energy balance across this surface, so I create a small stripe of size dx, which is reside at the distance x from the left face, and from there the total heat flux that contains or across this shaded area or control volume can be taken as QA dx, which is equal to the amount of heat flows across the left face and sum with the heat across this control volume on the right face, which is given by this much of the difference between the one that enter on the left face. So rearrange this equation so we can write the energy balance as the equation that we have at the bottom of the slide here, which is the heat that flowing into the control volume usually will have a negative signs, then the one that leaving the control volume will have a positive signs. So the QA dx plus QA, which is equal to Q plus the change in the heat flux across this control volume, which is given by dq over dx and multiplied by the area, where the term Q here refers to the heat flux per unit area, A, which is the area normal to the directions of heat flow, and the capital Q here actually refers to the internal heat generated in the control volumes. So solving this energy balance equation, then we will find that this Q, which is essentially equal to the gradients of Q in x directions. So now we have the equation number 1 there. So for one-dimensional heat conductions, it says that the heat flux itself is governed by the Fourier's law, which is it stated that the heat flux is actually just the gradient of temperature in one dimensions and multiplied by the thermal conductivity of a specific material, and all of this actually have the negative signs. So this equation here, the negative sign in this equation number 2 actually is to shows that the heat will flow from the high temperature to the lower temperature. So at this stage, then we know that Q, which is just the gradients of the Q over dx, and we also now at this stage that from the Fourier's law, that the heat flux, which is equal to the gradients of the temperature in one directions and multiplied by the material heat conductivity of a specific material. So these two equations actually can be put together by substituting this Q into this capital Q equation, yields these equations. So the internal energy, or the one that represented by the capital Q, may have the positive and negative value depending on its physical applications. For example, the positive value represent the system that is generating heat So, or sometimes we call it as a heat source, and the negative value actually to represent that the heat is consumed in the system, or we can call it as a sink. So now we have the two new terms, which is called as the source and sink to the heat generations. The equation that we have here can be solved, but it requires appropriate boundary conditions. So there are three type of boundary conditions to deal with the heat conduction heat transfer problems in solve it in finite element methods. So the first boundary condition, which is known as the specific temperature, that means at one particular nodal point, or usually on the face of our plane wall, we may know the temperature of that particular wall surface. B, which is known as the heat flux, and given by Q equal to 0, that means there is no heat flows across these regions or this face. So that means here on this left face of my wall, so this face is insulated. So that means here there will it is an insulator that is prohibits the heat to transfer into or leaving the this surface. And the third one here, which is known as the convections at the edge of the surface. So sometimes to help further to reduce further the temperatures, we can what we call it as we can force the convections on the surface, maybe by using fans, blow, or by flowing the certain liquid that will further cooling this surface or temperature on the surface. In this topic, we will limit our discussions on the one-dimensional elements only, which is to obtain reasonably good temperature distributions. We will discretize the wall that I have in this figure here into several 1D heat transfer elements. So considering this is my plane wall, that if in 3D it will look something like this, but since we are considering the heat will flows from the left to the right face of this plane wall, so we will discretize the wall in this x directions only. So similar to the very similar to the 1D bar problems as we look in the our earliest topic on the finite elements. So the way we discretize this plane wall is very similar to the 1D bar problems. So in this case, we just create this or we can model our plane wall as a straight element, which is assuming that this element will represent the temperatures distributions at each nodal point as it's progress from the left side of the wall to the right side of the wall. If we still can remember, when we solve structural problems in finite element, we are solving the simultaneous equations in the form of kq equal to f, where k is the element stiffness matrix of our geometries or structures, f is the applied loads that are applied to our structures, and q is the desired displacements to be determined once the load is applied to the structures. But for the heat transfer problems, we are solving the system of linear equations in the form of k t equal to r. So these two, they are actually a similar form of equations, but in this case, in the heat transfer problem, we are interested in determining the temperature distributions across our structures. And solving this simultaneous equation for T will give us the temperature at each nodal point. So for example, after solving the kt equal to r, then we actually are able to determine T1 and T2 along our finite elements model. Thus, to determine the temperature or temperature field within the two nodal points, the interpolations technique must be applied. So in this case, we'll limit our discussions to the linear interpolations as well, similar to the one that we discussed in the structural problems. So the temperature field, which is given by T in natural coordinate system Z, can be obtained by taking the linear interpolations N1 T1 plus N2 T2, where N1 and T2 refers to the linear shape functions, and this can be written in a more compact formats, which is in the matrix format T equal to N multiplied by T, where we know that N1 equal to half 1 minus z and n2 equal to half 1 plus z. So where z is the natural coordinate system, and in our course we use that z, which is always equal to -1 on the left hand side of our element, and z equal to +1, which is reside on for the node that reside on the right hand side of our elements. Then we recall back the heat flux equation, where we have Q equal to -k dt over dx, and we work a bit on this expression dt over dx, which is initially we are working on the Cartesian coordinate system. Then it is a very convenient to convert it into the natural coordinate system by first converting the term dx dt over dx by using the change rules. So dt over dx can also be expressed as dz over dx multiplied by dt over dz using the change rule of differentiations. And knowing that our natural coordinate system is given by these expressions, and differentiation of z by x, then we will get the second equation for the dz over dx that is required in these equations. And what is about this expression dt over dz? The dt over dz actually can be obtained from this field temperatures equation. So if we work a bit on this N1 T1 plus N2 D2, where we know the N1 and N2 is given by these two equations, then substituting these two equations into the field displacement field temperature equation and differentiates the T by the Z, then we will obtain the third equation, which is as shown here, where in this case, by using linear interpolations approach, we get the expression for the T over dz, which is given by negative half T1 plus half of the temperature at nodes number 2. And substituting this dt over dz into these expressions, then we can rewrite the new expression for the dt over dx, which is given by the equation that we have at the bottom of the slide, where the term x2 minus x1, which is actually representing the length of our elements that we consider in our analysis. So from the previous slide, we know that dt over dx, which is given by 1 over length of elements multiplied by negative T1 plus T2, and this equation can also be written in the a more compact format, which is in the matrix format, metric and vector format, which is by taking 1 over x2 over x1, and then we have the rows of vectors of negative 1 and 1 multiplied by the column vector of temperatures T1 and T2. So in even more compact ways, then we can take that this expression, the whole expression here, which is represented by matrix B. So, and this matrix B is called the temperature gradients matrix. So in this case, the heat flux Q can now be expressed in terms of Q equal to negative K multiplied by 1 over the length of elements and multiplied by negative 1 1 and multiplied by T1 and T2. In finite element, there are several approaches or methods that can be used in solving heat transfer problem. For example, we can determine or we can develop the element conductivity metric based on the Galerkin method, but in our case we will focus or limit our discussions on how we can develop the element conductivity metric using the potential energy approach. So if we recall that the conduction governing equations with internal heat conduction, which is given by this equation as we have seen in the previous slide, then if we impose the two boundary condition, which is the known or specified temperature, and also this is the convections boundary conditions to this our governing equation, and solve the equation, then it gives us the total energy, total potential energy, which is given by the equation that we have at the bottom of the slide here. If we substitute the terms dx and the term dt over dx with the one in the natural coordinate systems, so the term dz, which is now equal to 2 over x2 minus x1 multiplied by dx, and the term dx, which is equal to the length of element over 2 multiplied by dz. We also know as well that temperatures equal to the field temperature equal to the shape functions multiplied by the temperature initially calculated on each nodal points, and the gradient of the temperature in x directions or in one dimension is given by b multiplied by t. So assuming that the heat source Q equal to Q and QE and thermal conductivity K equal to KE, that means the thermal conductivity within our elements are constant within the element, then the function pi t will become as these equations. So in this lecture, I'm not going to derive or discuss in detail how we come up with this equation, but I encourage all the students will be able to come up with these equations by trying it yourself. So in these equations, we have the three terms that exist in this equation, potential energy equation, which is the first one, the second one, and the third equations. So the first equation as we obtained in this potential energy equation actually equivalent to the internal strain energy for structural problem, which we can use these equations to determine the element conductivities matrix. So the terms K, the element conductivity matrix, actually contains in the parentheses in the first term of this potential energy equations. So solving this integration from -1 to 1, from z equal to -1 until z equal to 1, so that means we are integrating these equations within our elements for the term bt transpose and bt multiplied by dz. Then we should be able to obtain the new expression for the element conductivity metric, which is given by this simple expression here, where for a 1D heat transfer problem of the temperature or heat across a plane wall, the element conductivity metric looks very similar to the one-dimensional structural problems, where we have the constants coefficients outside of the matrix here, and we have the square matrix of 2 by 2 with 1, -1, -1, and 1. So for the heat transfer problem, we have to include the thermal conductivity's value Ke over L, or the length of our elements, then multiplied by this square 2 by 2 matrix. So if I can recall the similar equation, the K for the structural analysis that we have done in our earlier of our lecture, we have a very similar form of the equation, where we have A E over L, and then we also have a square matrix of 2 by 2, 1, -1, -1, and 1. So this is how the similarity between the two when we are dealing with the one-dimensional problems. Again, it is very important to highlight that the elements conductivity metric that we have generated just now here is only applied or must be calculated for each element available within our structures. For example, if I have 4 elements as shown in these examples, so that means here I have to calculate the KT for each element here, then assemble it to form a complete systems. So at this stage, actually, we should be able to generate the global K matrix for our structures. Then the next step is to look at the terms R's in our simultaneous equations. In our heat transfer through a plane wall, the element's heat rate vector is actually depends solely on the internal heat generations QE within the elements. So as we can see here, it's mentioned that the element heat rate vector due to the internal heat generations is given by this equation. So that means here, if within my plane wall, if there is a heat generations exist or applied to my problem, then there will be a value to be substitute for the Q here, and there will be a value for the heat rate vector. So if there is no internal heat generations process occur in my system, which is that means Q equal to 0, then my heat rate vector will be 0 within the element that we consider. So in finite elements analysis, for example, I would like to determine the temperature distributions across my plane wall here. Then I purposely divide my plane wall into 3 elements. So this is my element number 1, element number 2, and element number 3, where as we can see here, there is a heat generated within the element number 2. So in this case, there will be a heat rate vector for the element number 2, where QE here will take the value of Q, and it will be divided by 2. That means the internal heat generation here will be transferred into the equivalence internal heat generations on both a nodal point number 2 and number 3 in this figure. If, for example, there are more than one elements in finite elements model, then the global heat rate vector is to be assembled as usual manner. It's similar to we assemble the applied loads, similar to we assemble the element stiffness matrix as we seen in the structure problem before. So now, since we have assembled our K matrix, and we have obtained our global R matrix, then we can rearrange this equation in this system of linear equations or simultaneous equations as shown by this equation KT equal to R, where K, T, and R, which is as given by these matrix equations, on the slide. But as mentioned here, at this point, the global system of linear equations have no solution. Why? Because we still didn't apply the boundary conditions to this simultaneous equations. So to solve this system of linear equations, boundary conditions must be analyzed first and later on apply to this system of linear equations, so that to make this SLE works. The first type of boundary condition is known as the temperature boundary condition. So this boundary condition is a type of boundary condition where we know the temperature on the surface of our plane wall. For example, suppose uniform temperature T, which is equal to theta degrees Celsius, is specified at the left or plane of a plane wall. So assuming that we know the temperature, which is uniform, apply on this left side of our wall, then to impose this boundary condition, then we have to modify the system of our global system of linear equation, which is initially that we know that our global system of linear equation, which is in the form of kt equal to r. In order to solve this system of linear equation, then we have to apply this the boundary condition. So let's say this is our system of linear equation, which is consists of K matrix, the unknowns T, temperature distributions, and this is the column vector R. So since we know the temperature which is specified on the surface of our plane wall, in this case where we begins our nodal point in terms of its numbering, starting from left to the right. So let's say I take it here as nodes number 1, nodes number 2, nodes number 3, and nodes number 4. So we know that now temperature apply to the nodes number 1, because we know the temperature T1, so we do not need to solve these equations anymore. So what we can do, we can eliminate the columns and row number, and that is referred to the nodes number 1. So what left here, which is all the coefficients, the unknowns and the knowns value for the R here for all nodes other than nodes number 1. But in solving the heat transfer problem using finite element method, once we eliminate the rows and columns, then we have to somehow modify the right hand side equation by including all the coefficients, the K values in the column number 1, and bring it to the right hand side of the equation, as we can see here, and then we multiply all the coefficients that we bring to the right hand side here by the angle, by the temperature, by the known temperature on the nodes number 1, or the temperature that representing on the surface, on the left surface of our wall. So this is how we can deal with the temperatures boundary conditions. So what will be happen, for example, if we have the specified temperature on the right hand side as well. So in this case, let's say I call it here instead of theta, I call it here as the beta. So that's mean here T4, which is also equal to the T on the last one, so we call it as a TL. So here actually will be equal to beta value, which is referred to this temperature at point number 4, or equal to TL. So in this case, similarly, once we know this, we know the value of the temperature beta, then we can eliminate the row and column for the last nodal point, or representing the point that reside on the right face of our plane wall. And again, once we have this a new boundary known boundary conditions on this T4, then we again have to bring this whole coefficients to the right hand side. So I have K1L here, and then I have KLL, and all of this will be multiplied by the angle beta. So this is how we can deal with the known boundary conditions applied on the surface, whether on the left or on the right hand side, or both sides of our plane wall. And suppose we would like to improve the heat release, or further improve the cooling process on the surface of our plane wall. So the convections by flowing the air by using, for example, fan, or by flowing certain cooling fluids on the surface of our plane wall can be done. And in this case, the convections boundary conditions can be applied. So it's mentioned here that suppose that convections occur on the right side of a plane wall, which is at x equal to L. So again here, if I can draw my finite element model across my plane wall, and I have, for example, 3 elements there, and this convection process occurs on the T L or T equal to 4, for example, taking that this is the directions of my x-axis. So this will be T1 for the nodes number 1, and this is the node number 4. I can call it TL or T or T4 in this case on the surface of this right face of the wall. So the effect of convection can be incorporated by modifying the global system of a linear equation. So in this case, we have, for example, set up the system of linear equation in the form of kt equal to r. And now our problem is involving this convection process. So in this case, to solve the system of linear equation, the convection boundary condition can be included in the system of linear equations by modifying the system of linear equation to the last, as we can see here, to the last of our coefficients in the K matrix by adding it with the convection heat transfer coefficient H, and for the right hand side equation, then we have to add the heat rates vector R with the convection's heat transfer coefficients and multiply by the convections or the ambient temperatures where the convections occurs. Furthermore, if the convections occurs on the right hand side of the face, on the left hand side of the face as well, with given that T equal the convection temperature T and the convection's heat transfer coefficient H, then the system of linear equations should be modified to the first elements or coefficients in the K matrix, and also to the heat rates vector by including the T and H to the first equation. The last boundary condition that involved in the heat transfer problems, which is in the type of heat flux boundary conditions. So for example here, suppose the heat flux Q equal to Q naught is specified at the left side of the plane wall, which is at x equal to 0, which is somewhere there. Or these heat flux boundary conditions can be applied where we know the how much the heats are flowing from maybe from the outside or from the ambient into the control volume or into our systems. And maybe if, for example, there is insulations occur to prevent the heat to flowing or leaving the system, then we know as well that the heat flux for the insulations process, then there will be no heat flowing across the insulator. So in this case we know that Q will be equal to 0. So the effect of specific heat flux can be incorporated into the system of linear equation by modifying the right hand side equations of the system linear equation as shown here. So we have the K global here, and this is our global temperature, which is the unknown that we would like to determine. So this is the heat rate vector, which is calculated based on the internal energy that may develop or may exist in our system. Then if the heat flux boundary condition is to be included, then we have to add this the heat flux influence to the right hand side equation as shown here. So in this example where we have the heats that flowing into the system, then we will have the heat flux with the negative value. For the process where the heat is flowing or leaving the system, then we will have the positive value for the Q. So this is how we can use the finite element method in solving the heat transfer problem across a plane wall in one-dimensional, and by treating different type of boundary conditions, then we should be able to solve the system of linear equation, which is in the form of Kt equal to R. So to help us understand the process of solving heat transfer problem using finite element method, let's look at the first example that we have on this on the slide here. So in this problem, assuming that we have a composite wall as shown in the figure here, where this wall is made up of three different layers of materials, where each of these materials have the heat transfer coefficients as given in the slide here. And on the right surface of this wall, which is exactly on this surface of the wall, then we know the temperature on this wall, which is given by 20 degrees Celsius. On the left hand side of the wall, then we have the convection process occur, where the convection temperature is 800 degrees Celsius, and the convection heat transfer value is 25 watt per meters square per degree Celsius. So the size or the thickness of each layers is as shown here. The material number 1, 0.3 meter thickness, material B, material number 2 and number 3, they are both having 0.15 meter in their thickness. So this is the physical problems or the physical geometries of our plane wall. So to solve this with the finite element model, so I can draw the a one-dimensional finite element model and discretize this my composite wall based on their material. So this is one of the most easiest way to solve the heat transfer, where we have a block that made up of a different material. And so this the similar finite element model can be represented by the figure that we have at the bottom here. In order to solve that particular problem, so we should have in our mind that this is the system of equation that we are required to solve. So in the first place is to dealing with the K matrix. So since our system consists of three elements of different materials, then the K or the element connectivity matrix must be calculated for each element. So in this case, we calculate the elements connectivity matrix to the elements number 1, element number 2, and element number 3. So as usual, it is very good to write the element connectivity on our matrix for each element. So if I can write it 2, 3, 2, 3, and here I have 3, 4, 3, 4. So the largest index that I have here should be equivalent to the largest nodes numbering that I have in my systems. So once we have calculated the elements conductivity metric for each elements, then again we have to assemble all these three element conductivity metrics according to their indices, or I can call it as the address as well. So for the whole complete system, or for the whole composite wall, then the elements conductivity metric will be like this. So we will have a 4 by 4 square metric systems with this matrix has the diagonally symmetric between the upper part and the lower parts. Once we assemble the elements conductivity matrix to make a whole system, then we can rewrite it in the global system of linear equations as shown here. So for the heat rate vector R or R vector, and since there is no internal heat generations occurs in our system, then the all term for the R will be equal to 0. So at this stage we can replace the heat rate vector with all the zeros value, but up to this stage the boundary condition is still not included. So if we go back to our problems, which is we have two types of boundary conditions should be considered, which is a specified temperature on the right surface of our wall, and also the convection process on the left hand side of our wall surface. So from there we first start with the dealing with the specified temperature boundary condition, which is given by the on the notes number 4 equal to 20 degrees Celsius. And in this case, since we know the temperature on the notes number 4, then we do not need to solve this equation anymore. So in this case we can eliminate the rows and columns for this equation number 4. And since we eliminate the column number 4, then we have to take this coefficient and bring it to the right hand side of the system of linear equation. At this stage our right hand side equation should be read as 0 0 0 0, which is this is our heat rates vectors R, and then we have these all coefficients which is we transfer to the right hand side, which is we have 0 0 -5 and 5, and then all of this must be multiplied by 20, and furthermore we have another boundary condition, which is in the form of convection process. So this convection process occurs on the left hand side or left surface of our wall, which is referred to the point temperature number 1. So in this case this part here is actually came from initially we have 1 there, 1 plus we plus by the convection heat transfers value, which is 25, and in this case we have to divide it by 66.7. So we will get 0.375 plus 1, then we have 1.375. So in this case you have to be very careful when we are working with convection heat transfer, where we have to modify a single element in our K matrix, and especially when we have a constant value outside of our matrix there, then you have to divide by the constant value, so that it will be so that you can include the correct values in this metric coefficient there. So in that case here For the heat rates, for the convective process, then the right hand side equations must be modified so to include the H multiplied by T to our first equation, which is in this case our H equal to 25 and multiplied by 800. So what we have in the slide here, which is actually the summations of all of these components here, where if you look at the first value in our right hand side equation contains 25 multiplied by 800, which is essentially refers to H multiplied by T plus 0 minus 0. For the second equation, we have all zeros, then we have all zeros there. For the third equation, we have 0 minus 5 multiplied by 20 and multiplied by 66.7, and plus 0. And for the last equations, we have for the equation number 4, so the right hand side equation will be 0 minus 5 multiplied by 66.7, then we bring it to this right hand side, and then a plus with the 0, which is that means there is no convection occurs on the right surface of our plane wall. Having this system of linear equations with all the boundary conditions set up, then we actually now are able to solve the system of linear equations to find for the unknown temperature at nodes number 1, nodes number 2, and nodes number 3. Then this can be solved by using Gaussian eliminations or Gauss-Seidel methods, or any system of linear equations solver in order to solve for these unknowns. Or you can substitute all of this value into the MATLAB or into the Octave to determine the all unknown temperatures. So this is the temperature at each node point after we solve the equation simultaneously. Then from there we can roughly say that let's say I take the x-axis is refers to the nodes numbering. So nodes number 1 located there, nodes number 2, nodes number 3, and nodes number 4. And from there actually I can plot the temperature distribution across the plane wall that was developed based on layers of 3 different materials. So this is not to the scale, so this is the first temperature, which is 304.6 at nodes number 2. So the temperature dropped quite drastically to 109 degrees Celsius, and then it dropped about half of the temperature at nodes number 1 to 57.1, and then it dropped about half again at nodes number 4, which is dropped to 20 degrees Celsius. So we can somehow combine this plot here using the linear curve. Then this is actually representing how the temperature distributions or distributed across the our plane wall that we consider in this example. Alright, I think that's all for our discussions on this finite elements method for solving steady state one-dimensional heat transfer problem across a plane wall. Thank you very much.